Okay, now we can start talking about the auditory and vestibular systems. These are examples of what are called the mechanical senses. Mechanical sense is just a sensory system that is used to detect a mechanical stimulus. So mechanical stimulus is pretty much what it sounds like. It's any sort of physical force or deflection of some part of the body or sensory receptor. So sound is an example of a mechanical sense because sound is just the movement of air molecules that are detected by deflection of special cells in the ear, which we'll talk about soon. The vestibular system is also a mechanical sense because it's your sense of the position of your head and the movement of your head, and that's detected by a sensory stimulus that's kind of similar to sound. In fact, it's connected to the same uh, it's part of your inner ear. We'll talk about that. The proprioceptive system is a little bit more complicated. We're not going to talk about it as much until we get into the motor systems, because this is your sense of the position of your body essentially in space and in relationship to itself. So it involves the measuring the tension of muscles and the angle of joints, etc. And then in the next chapter, actually, we'll talk about the somatosensory system. And for the most part, this is your sense of touch, and but it also includes pain and itch. But touch, of course, is a mechanical sense because you're talking about physical force against the skin. So, uh, but for now, let's talk about sound. So again, sound essentially is just the movement of air molecules, or the movement of water molecules if you happen to be underwater. But for us, for those of us that live on land and we're able to detect sound traveling through air, we're we're feeling the movement of air molecules. So a sound wave is kind of like a light wave in that it is just a traveling oscillation of air pressure instead of electromagnetic fields. And so a sound is produced by pretty much anything that causes air to move. So a stereo speaker, for example, is basically just a paper cone, usually, that has a little magnet attached to the bottom. And that magnet is attached to a piece of metal that is then attached to a wire, which connects back to your stereo. So when the stereo wants the speaker to make a sound, it applies a current. That current causes the magnet to move in and out with the frequency of the sound, and that little cone pushes little puffs of air out in front of it. And so a sound wave is basically just little puffs of air, this region of compressed air interspaced with regions of rarefied air. So that's all a sound wave is, and so that sound wave travels as air molecules kind of push each other forward through space. So sound has some analogous properties to light, but obviously has some important differences. One, sound travels much slower, so the speed of light is 3 times 10 to the ninth meters per second or thereabouts, whereas sound only travels in air about 300 meters per second. Um, and the other difference is light travels or can travel through a vacuum. In fact, it travels fastest through a vacuum, whereas sound can only travel through a medium. So there is no sound in a vacuum. So all those science fiction movies where you see spaceships blowing up or hear spaceships blowing up and hear laser blasts going off, that's one of the many problems with those movies. But you would not be able to hear those things in space because there is no medium for the sound wave to travel through. Uh, and so as a sound wave travels, it again has to move through a medium. In fact, the another thing that's different from light, light slows down as it goes through denser medium. So as it goes through water and glass versus air, but sound actually travels faster through more dense medium. So sound actually travels relatively slowly through air and more quickly through water and through solid. But it does not transmit very well from one medium to another. That's why if you've ever tried to swim underwater or hear while swimming underwater, it's hard because the sound has to travel through the water and then hit the surface of the water from the air, and it loses a lot of energy that way. But otherwise, sound acts like a wave, and so it has a frequency, just like light, although for whatever reason, sound is usually described in terms of frequency, whereas light is usually described in terms of wavelength. So a low frequency sound would have, we describe as having a low pitch. Pitch is basically the perception of changes in frequency. So low pitch means low frequency, high pitch means high frequency. And frequency has units of cycles per second. It's just a number of these little wave cycles that pass any given point in a given amount of time. So 1 cycle per second is 1 hertz. So that's how sound frequency is usually detected. And then a sound wave also has an intensity, which is just the amplitude of this wave, meaning the difference in pressure between the regions of compressed air and the regions of rarefied air. The louder the sound, the higher the intensity, and so the greater the difference there is between the rarefied and compressed regions. And we measure intensity of a sound as volume, and the units for that are decibels. So the ear, of course, is the organ that we detect sound with, and the ear has 3 regions: the outer ear, the middle ear, and the inner ear. The outer ear is pretty simple. It consists mostly of the part you can see is this big fleshy flap called the pinna. That's what that structure is actually called. The pinna is kind of interesting because it, for one thing, only really exists in mammals. So most other animals that have an auditory system don't have any sort of external structure for. So the pinna is only really found in mammals. Most other vertebrates that have an auditory system don't have any kind of external feature of the ear. So the pinna is important, as we'll learn later, for detecting where a sound came from. But otherwise, its job is mainly to just funnel sound into the auditory canal. So the auditory canal is just an air-filled hole that lets sound go through, sound waves travel through, and the auditory canal ends in this membrane called the tympanic membrane. And so that's also called the eardrum. In fact, that's why it's called the tympanic membrane. Anybody in band probably knows what a timpani is. That's a type of drum, and that's why it's called that, because this membrane is basically stretched very tightly across the base of the auditory canal, or at the end of the auditory canal, kind of like the skin on a drum. Because as a sound wave enters the auditory canal, when it hits the tympanic membrane, it will cause the tympanic membrane to vibrate at the same frequency of the sound. So every time there's a sound wave traveling in, the compressed air will push the tympanic membrane in, and the rarefied air will pull the tympanic membrane out. And that causes the vibration to be transmitted to the next chamber, which is the middle ear. So this is a closer up view of the middle ear. Basically, the middle ear is another air-filled chamber, but it is, and it's actually connected to your nasal cavity and your pharynx, your throat, by this little tube called a eustachian tube. So the air that's inside the middle ear actually comes from your nose and throat cavity, and that's important because the air pressure across the tympanic membrane needs to remain constant. In other words, you want the air pressure inside the middle ear to be the same as the air pressure on the other side of the tympanic membrane in the auditory canal. And that's because if it was not the same, in other words, if let's say the air pressure inside the middle ear was higher, then when a sound wave hits the tympanic membrane, it wouldn't be able to push it inward and transmit that vibration as effectively. And in fact, you may have experienced a differential in pressure across the tympanic membrane. If you've ever flown in an airplane, you may have had that sensation of getting to altitude and feeling some pain or pressure in your ear. That's because when you fly in an airplane, of course, once they get up to altitude, they have to lower the air pressure inside the cabin because air pressure goes down as you go up in altitude. Now they don't lower the air pressure as much as they would, as much as the external air pressure, but they lower it pretty well below what it would be at ground level. And that lowered air pressure is going to affect the auditory canal first, and the eustachian tube is continuous with the pharynx, but it is sometimes closed. So there are muscles that allow it to close. So sometimes it takes a second for the air pressure to kind of equilibrate, and in that time you'll have higher air pressure inside the middle ear than outside, and that is enough to press outward on the tympanic membrane and cause pain. Of course, also the tympanic membrane can become damaged or punctured, and that will prevent sound from traveling to the middle ear because it prevents the pressure from pushing in or out on the eardrum. So an air pressure wave that hits the eardrum would just pass through that hole. And then that's what happens if you puncture your eardrum. Usually, the eardrum, the tympanic membrane has the ability to heal. So if that does happen, it's usually not permanent. But that is one of the reasons why you don't want to damage your eardrums. But the real reason for moving the tympanic membrane is to move these little tiny bones that are inside the middle ear that are called the middle ear bones. These are the smallest bones in your body, and their job mainly is just to transmit the sound wave from the tympanic membrane to the inner ear, which we'll talk about in a minute. So there are three of these bones. The one that's directly attached to the tympanic membrane is called the malleus. So this is the malleus here. And then that is right next to this little bone called the incus. Now the incus and the malleus aren't really attached to each other. So when the malleus vibrates, so when the tympanic membrane pushes in this way, it causes the malleus to kind of swing back and forth. So the malleus swings backward when the tympanic membrane pushes forward. And then when the tympanic membrane pulls back in, the malleus swings toward the incus and kind of bangs on it. In fact, the word malleus and incus, the word malleus comes from the same root as the word mallet, like a hammer, and the word incus comes from the word for anvil, because that's kind of how they operate, a hammer kind of banging on an anvil. But then the incus causes this bone right here called the stapes to vibrate. And the stapes has this kind of horseshoe shaped, and that in fact, or actually, the word stapes comes from the word for stirrup, because that's also what it looks like, a little stirrup on the side of a horse's saddle. But the vibration of the stapes causes the vibration of this little membrane called the oval window, which is part of this structure called the cochlea, which we'll talk about in a second. So the middle ear bones, all they do is just transmit sound from the tympanic membrane to the oval window. Now you might wonder why you need these little ear bones to transmit sound, because if the sound wave can vibrate the tympanic membrane, why couldn't it just directly vibrate the oval window? But like I said before, one of the problems with sound is that it travels through air and water, but if it transfers from one to the other, it loses energy. So the inside of the cochlea is filled with fluid, as we'll see, and so if a sound wave were to directly hit the oval window here, the energy from that sound wave wouldn't be enough to really transmit the vibration into the cochlea, into the fluid of the cochlea. So the middle ear bones, their job is to basically amplify the sound wave, the intensity of the sound wave, enough to be effectively transferred to the interior of the cochlea. Another component of the middle ear, and this just kind of shows the order that things are connected. So like I said, sound travels from the auditory canal and then vibrates tympanic membrane. Tympanic membrane vibrates the malleus. Malleus vibrates the incus. Incus vibrates the stapes, and then the stapes vibrates the oval window. And that's the path sound takes through the middle ear. One other feature of the middle ear are these little tiny muscles. This one here is called the tensor tympani. So it actually attaches to the malleus, and then the stapedius muscle attaches to the stapes. These muscles are actually there to dampen sound waves. So when they contract, they apply tension to the middle ear bones actually kind of prevent them from vibrating, and that reduces the amplitude of sound waves. And these muscles are triggered whenever there's a very loud sound that gets to your ear. In fact, this is an example of a reflex. So a very loud sound would send a signal to the brain, and then the brain would send a signal back to those muscles to contract and kind of dampen it. So their job is mainly to prevent damage, because a very high intensity sound can actually cause damage to the middle ear, or more likely and even worse, to the inner ear. So that's sort of a protection mechanism for the ear. But then the actual organ that detects sound is this thing called the cochlea. So the inner ear consists actually of two parts. The cochlea, which is this kind of spiral shaped structure, it's cut in down the middle here. So this right here is what the cochlea looks like when it's not cut. It's sort of like a snail shell. In fact, that's what the word cochlea means. It's just a spiral shaped tube. And then this other structure is called the labyrinth. And the labyrinth, or the vestibular labyrinth, is the organ that is the sensory system for the vestibular system. And so we'll talk about that later. But they are connected. They actually share the same fluid. They're continuous with each other, and there are some similarities in how they transduce their respective stimuli. So that's why they kind of go together. But for now, we're just focusing on the cochlea, because that is the sensory organ for sound. So like I said, the cochlea is really just a long tube that's wrapped around in a spiral. And if you were to cut through that tube at any given point, what you would see inside is that it consists of three separate chambers that are sort of stacked on top of each other. The uppermost chamber, which is connected to the oval window, remember that's the window that the stapes is attached to, is called the scala vestibuli. And then the lower chamber is called the scala tympani. And then actually I think I have that backwards. The upper chamber, scala vestibuli, is attached to the round window. The scala tympani is connected to the round window. And then it'll become clear in a minute. And then the chamber in between is called, as you can see here, the scala media. In fact, that media just means middle, because it's in between the other two chambers. And these chambers, all three, wrap around the central axis of the cochlea in a spiral. So if you were to unwind the coil of the cochlea, which we can't do because the coil is actually wrapped around a little piece of bone called the modulus. It's kind of embedded in the skull. But if you could unwrap it, this is what it would look like. It's sort of a almost cone shaped. And the two windows, the oval window and the round window, if they're arranged this way, would be above and below. So the oval window is connected to the scala vestibuli, and the round window is connected to the scala tympani. So here's oval window up here, scala vestibuli here, round window down here, scala tympani down there. And what separates those two chambers, in addition to the scala media, you can kind of see if we go back to the cross section again, is this membrane in between called the basilar membrane. So the basilar membrane is what separates the upper and lower chambers of the inner ear, of the cochlea. And that's also the membrane that the actual sensory cells are found on. So we'll talk about in a minute this structure right here called the organ of Corti, and it contains the hair cells, which are actually going to detect sound. But the important thing about the basilar membrane is that it stretches all the way from one end of the cochlea to the other. The end of the basilar membrane that's closest to the two windows is called the base. So this is the base of the basilar membrane, and up here is the apex of the basilar membrane. And there is a little hole up here at the apex where the two chambers are connected, so fluid can go from one side to the other, called the helicotrema. And then, so the idea is that when the basilar membrane vibrates, it's able to vibrate up and down whenever a sound wave enters the cochlea. So remember that the stapes is vibrated by the other middle ear bones, And so whenever the stapes pushes in, it creates a pressure wave that travels through the lymph, what's called the perilymph. That's the fluid inside both chambers. And that pressure wave travels along the basilar membrane, causing it to move up and down. And that vibration, that up and down movement of the basilar membrane, is what the hair cells on the basilar membrane detect. And so the degree to which the basilar membrane moves is partly a function of its shape. So the base and the apex of the basilar membrane have slightly different properties. The base is actually slightly narrower, even though the chamber itself is larger. The base of the basilar membrane is narrow and relatively stiff, meaning that it takes a little bit more to cause it to move. And simply because of its shape, the maximum deflection a given sound can cause in the base is higher for higher frequency sounds, whereas at the apex, the other end of the basilar membrane, the apex is wider and a little bit floppy, meaning that it's easier for it to deflect. And so it's deflected by lower frequency sounds. Lower frequency sounds can cause a greater deflection of the apex. And so that actually is what determines the frequency range that you can hear. So different parts of the basilar membrane respond to different frequencies, and that is why there's a range of frequencies we can hear. So the upper frequency, the upper limit of what you can hear is determined by the base, and the lower limit is determined by the apex. And so for humans, the human hearing range supposedly is between 20 and 20,000 hertz. Now you can kind of get a sense of what that feels like. So this sound right here, hopefully you can hear that. That is 1,000 hertz. So that's kind of a really high B note. And so I can adjust this. I have a little slider here, all the way down as far as I want, and you can hear it getting lower and lower. So that's 20 hertz. And so probably you can't hear that. I can't hear anything at that frequency. I can see on my little audio meter that it's still playing sound, but there's nothing that I can hear. I don't hear anything until I get to about 40 hertz. So at 40 hertz, I can hear a very low frequency sound. I can't hear it very clearly until I get up to 60 or 70 hertz. At the upper end, so that's 20 hertz. Again, I can't hear any sound at all at that frequency. I don't hear any sound until I get down to about there. So that's about 12,000 hertz. And actually, that's another interesting thing. So the human hearing range again is dependent on the properties of the basilar membrane. So different animals, different species could have a wider or narrower hearing range depending on the properties of their basilar membrane. But it turns out that the properties of the inner ear change with age as well. So those higher frequencies actually become harder to hear as you get older, because the hair cells at the very end of the base are the most sensitive and easiest, or most delicate, I should say, and so they can die as you get older due to extremely loud noises. And so as you get older, the highest frequency you can hear goes down. So again, I can only hear up to 12,000 hertz. You guys might be able to hear well above that, maybe into 16 or 18,000 hertz. You guys can let me know later. Anyway, like I said, the real important part of the cochlea is this thing called the organ of Corti. So the organ of Corti just sort of sits on top of the basilar membrane inside the scala media, and it's surrounded by fluid as well. And it sits between the basilar membrane and this structure here called the tectorial membrane. The tectorial membrane is kind of like a shelf that just sticks out into the scala media, It's attached to the modulus. Remember, the modulus is this bone over here. And so the tectorial membrane is essentially rigid. It doesn't move. But the basilar membrane does move. And so the up and down movement of the basilar membrane causes these little cells that are sitting on top of the basilar membrane called hair cells to move. So these hair cells are the actual cells that detect sound. They have these little tiny projections called stereocilia. You can see them here on the inner hair cells and here on the outer hair cells. In a minute we'll talk about the difference between the inner and outer hair cells. But for the most part, their job is to just detect the vibration of the basilar membrane that then causes the movement of these stereocilia to move back and forth. So because these are the sensory cells for the auditory system, the axons that synapse with them come from a spiral ganglion that's right outside the cochlea. So you can kind of see that if we back up to well, you can kind of see that this bundle of nerves are the axons that are eventually going to find their way to the spiral ganglion, and then the spiral ganglion neurons. Their axons come out and form the auditory nerve. So the auditory nerve then goes back to the brain. So that's how information gets from the ear to the brain. Like I said, the job of the basilar membrane is just to move up and down. So as a sound wave travels along the cochlea, it causes the basilar membrane to vibrate. And so when the basilar membrane is deflected up, it causes those stereocilia to be deflected outward, essentially, so away from the modulus. And then when the basilar membrane is deflected down, the stereocilia are deflected the other way, towards the modulus. So they sort of sway back and forth at the frequency of the sound wave. There's one other structure here. This layer that sits on top of the organ of corti is called the reticular lamina, which is attached to the basilar membrane by these sort of semi-rigid rods of corti, and they're just there to make sure that the upward pressure of the basilar membrane actually pushes the hair cells around instead of just sort of squishing them. And then of course there are also some support cells in here that are important for keeping the extracellular fluid around the hair cells intact. So